In this optimization example, we are trying to find the point on the line y equals 1/2 x plus 1 that is closest to the given point 2, 0. And so for these optimization problems, we have a bit of a procedure like find the objective, find the constraint, write your equations and things like that. And it's good to follow that procedure if you're unsure about what to do next. But here we can just kind of jump right in and maybe try to draw a picture. So we have this line, y equals 1/2 x plus 1. That's just going to be a straight line with a y-intercept of 1 and a slope of 1/2. So for every 1 we go up, we go over 2. And so our line, y equals 1/2 x plus 1, is going to look something like this. And then we're trying to find the point on this line that is closest to this given point of 2, 0. So maybe our point 2, 0 is right here, and we're trying to find the point on our line, the x and y coordinates, that make it so the distance between that given point 2, 0 and that point we're trying to find is as small as possible. And so by drawing this picture and reading the problem, we know what our objective is. Our objective is to minimize the distance between some point on our line and this point 2, 0. Well, then we can use our distance formula. Remember, the distance formula says the distance between 2 points x1, y1 and x2, y2 is given by that kind of Pythagorean theorem formula. It's going to be the difference between our x value squared plus the difference between our y value squared. We add those two quantities up and take the square root, and that gives us the distance between any 2 points. And an important fact that we're going to use here to make this problem a bit easier, if you want to minimize or maximize a distance, it's equivalent to minimizing or maximizing the square of the distance. So here we can actually minimize or maximize what I'm going to call capital D, which is really just the square of our distance. Our constraints are kind of also included in this picture we drew over here. The constraints are one of our points has to be the point 2, 0. Our other point, xy, has to satisfy the relationship that y is just 1/2 of x plus 1. So now we can put the information we found for our objective function and our constraint information together to create the equation we actually need to work with to minimize the distance here. And really remember, we're minimizing the square of the distance. So our equation that represents the square of that distance is going to look like d is equal to this quantity. But we need to express this quantity eventually in terms of just a single variable, x or y. So it's the difference between these x values squared plus the difference between these y values squared. Let's go ahead and call our point xy, x2, y2. And our given point 2, 0, that'll play the role of x1 and y1 in our formula over here. Then if we plug this information into the square of our distance formula, x2 minus x1 ends up looking like x minus 2. Remember, we have to square that quantity and add to that the difference between our y values also squared. So y2 minus y1 is just going to look like y minus 0 squared, or just y squared. So now our distance formula, or really the square of our distance formula, looks like x minus 2 squared plus y squared. But here's where we want to stop and see if we can write this as a single variable function instead of a function of two variables, x and y, that we have at the moment. And we can do that because we have this constraint that point xy that is in play here has to satisfy the relationship that y is always 1/2 of x plus 1. So instead of looking at y squared, we can look at 1/2 of x plus 1 squared. All right, with all the work we've done so far, we've just reduced this kind of abstract optimization question, this word problem, down to now just a more familiar max-min problem. Now we're just trying to find the minimum value of this function. So let's go ahead and do just that. Right, this should be pretty procedural at this point. To start finding our minimum value, we first have to find our critical numbers. So we have to find that first derivative to find those critical numbers. Here we could expand everything to help us find our derivative, but I'm just going to use the chain rule instead. So to find the derivative of the quantity x minus 2 squared, we got to use that chain rule or generalized power rule. Bring the exponent out front. So bring that 2 out front, decrease the exponent by 1. We have to multiply by the derivative of what's inside, but the derivative of x minus 2 is just 1. So that takes care of differentiating that first piece of our distance formula, or really the square of our distance formula. We now have to differentiate the second piece. So we'll have to add to this the derivative of the quantity 1/2 x plus 1 all squared. Again, we can find that derivative using the generalized power rule. Bring the exponent out front. Decrease the exponent by 1. So just that so far is giving us 2 times the quantity 1/2 x plus 1. Then we have to remember to multiply by the derivative of what's inside. And the derivative of the inside of our function is the derivative of 1/2 x plus 1. And that derivative is just 1/2. So that 1/2 factor will actually cancel out that factor of 2 that we saw in our earlier step. So now to find our critical numbers, we have to set our first derivative equal to 0. And here's where I would take some time to expand it and combine like terms. If I expand that first quantity, we end up with 2x minus 4. And the second quantity is just 1/2 x plus 1. So now if I solve this equation for x, first I might have to move all the constants to the other side. So I'd add 4 and subtract 1. That'd leave me with 3 on the left-hand side. If I combine these like terms for x together, 2x plus 1/2 x gives us 2.5 x, or 5/2 x. So now to find our actual x value, we have to multiply both sides by 2/5. So x is going to be equal to 3 times 2/5, or 6/5, or 1.2. So we now know this critical number for our function. We still have to verify if this critical number actually corresponds to a minimum, since that is our goal here, to minimize the distance. And well, we can do this in a couple ways. We could use our first derivative test or our second derivative test, or we could recognize, well, the equation we are working with is a quadratic equation, right? We have an x squared and then another x squared, and it's going to be a concave up quadratic equation. So we know there's going to be a minimum, and the only critical number for this quadratic function is going to correspond to that minimum. So we can kind of skip some of those steps we usually have to do for verifying our critical number actually is a maximum or a minimum. But we still have to make sure we answer the original question. Remember, the original question asked, find the point x and y on our curve 1/2 x plus 1 that is closest to the point 2, 0. All we found so far is the x coordinate of that point. We still have to find the y coordinate. But that's not too hard to find because we know y is just 1/2 of x plus 1. So if x is 1.2, y is going to be 1/2 of 1.2 plus 1, or 0.6 plus 1, or 1.6. So our final answer, the actual point xy that minimizes the distance from our curve to the point 2, 0, is going to be the point with an x coordinate of 1.2 and a y coordinate of 1.6.